recording? It is. Okay. In real situations, when we're doing a study, we usually sample several individuals from the population and calculate some kind of numerical summary. The most popular numerical summary is the sample mean. Now, if I grabbed a sample of people from over here and a sample of people from over here, are they going to have the same mean, do you think? One sample here and one sample here? They're probably going to have different means. But if I kept drawing samples, I mean like a sample, a whole bunch of samples, and I took the mean from each sample, then those are all going to be a little bit different, right? If we take all of the means from every sample possible from a population, we can make a probability distribution for that. And it is called the sampling distribution. Of the means. So if I have all of these averages from every single sample, they're all a little bit different. But guess what happens if I take all of those means and I average them together? The mean of all of those samples, it's denoted by, so we got the mean of the sample means. So this is if I average every single sample mean, it is going to actually give me the population mean. So if I have enough samples and I get the average from every sample and I average those, I'm going to get the true mean for the population. Pretty nice. Now, the standard deviation of this sampling distribution, and so it's denoted with the pregnant 6 with an X bar. That means it's the standard deviation of my sample means. It is not exactly the same as our population standard deviation. What it ends up being is the population standard deviation divided by the square root of n. And what n is representing, n is the sample size. All right, so let's say we have students at a certain college. The mean number of hours of television watched for that college is 10.5. That's a population value. Notice it doesn't have any subscript. If it doesn't have any subscript, this is from the population. Same thing here. This is population data. So population data is that the population mean is 10.5 and the population standard deviation is 3.6. Let's say we have a simple random sample of 16 students that are chosen for a study of viewing habits. And X bar is the mean number of hours of TV watched by the sampled students. Find the mean of the means. So mean of the means. Well, I love it that the mean of the means is equal to the mean. The average of all of my means is going to be equal to the population mean. Well, what's the population mean? 10.5. Now, the standard deviation of those samples is going to be a little different than the population standard deviation. We take the population standard deviation divided by the square root of the sample size. So the population standard deviation was 3.6. And we're going to divide by the square root of, what was our sample size? 16. So this is the n is 16. So 3.6 divided by the square root of 16. I don't know where my calculator went. 3.6 divided by the square root of 16. 0.9. Perfect. Thank you. Are we okay on using those formulas? Awesome. All right. Now, if I try to get a sampling distribution from a skewed population, so skewed, which way is this one skewed? Skewed right. If my sample sizes are the size 3, it's still really skewed, right? If I move to a sample size of 10, we notice it's starting to get a little bit closer together, but it's still a little bit skewed. What happens when I reach a sample size of 30? What do we call that picture? Normal. So a sample size of 30, if n is bigger than 30, the sampling distribution, well, I guess I need to write that in the right place. Oh my goodness, I'm having one of those days. Here, we'll write it big here. This is called the central limit theorem. If n is greater than 30, then the sampling distribution, in other words, the distribution of every possible sample we could have in the world, sampling distribution, is approximately normal. If it's approximately normal, then we can use that normal distribution on the calculator and find all kinds of probabilities and stuff like that. Now, in the calculator, the mean we're going to use, so the mean of the sampling distributions is equal to the population mean. And the standard deviation we're going to be putting in the calculator is going to be the population standard deviation divided by the square root of n. So first we need to think about on each of these next examples, is it going to be appropriate to use a normal distribution for the topic or not? So a sample size of 45 will be drawn from a population with a mean of 15 and a standard deviation of 3.5. Is it appropriate to use the normal distribution to find probabilities? Why? N is bigger than 30. A sample size 8 will be drawn from a normal population with mean of -60 and a standard deviation of 5. Now, notice the key word there. It said the population was already normal. If the population is already a perfect curve, then any sample I get from it is also going to be normal. So because the population is normal, so if they tell us the population is normal, we can use the normal distribution. So there's going to be our two definite reasons we would use the normal distribution. N is greater than 30, or they better tell us that it's from a normal population. Normal population means it's a perfect little bell curve. All right. A sample of size 24 will be drawn from a population with mean 35 and a standard deviation of 1.2. Can we use a normal distribution on that one? No. Okay, so there's two reasons we can say no. The sample size is less than 30, and we don't know if the population is normal. If the population is skewed, that sample size has to be bigger than 30 for us to use the process. So if they tell us it's normal, everything's normal. Yay. If it doesn't tell you it's normal, we have to make sure the sample size is bigger than 30. All right, so now we're going to use those things, and we're almost done with the notes today. All right. Recent data from the U.S. Census indicates that the mean age of college students is 25 years with a standard deviation of 9.5. Notice that those don't have subscripts. So that means that's from the population data. The population data says that the population mean is 25 and the population standard deviation is 9.5. A simple random sample of 125 students is drawn. So N is 125. Are we good under the assumption? Did they say we were normal? No, but is our sample size big enough? Cool, so check. We want to find the probability that the sample mean age is greater than 26. Now, what we're going to put in the calculator, we need to find the mean of the means and the standard deviation of the means. Well, what was the mean of the means? 25. It's the same as our population mean. But the standard deviation, we have to make a little bit of an adjustment. It really depends on that sample size. So we're going to take the population standard deviation divided by the square root of n. So we're going to take 9.5 divided by the square root of 125. So let's take 9.5 divided by the square root of 125. And I got 0.8497. And I'm going like 4 decimal places because I want this to be as exact as I can. Now, we can use this information in the calculator to find that probability. So let me see if I can put my calculator up here. So where am I going to go to find a probability for a distribution? Distribution. Which one am I allowed to use right now? Normal. What mean am I going to put in? 25. And the standard deviation, we're trying to find the standard deviation of the means because we're not doing a probability of a certain individual. We're trying to find the probability that a mean of a sample is greater than 26. So we're going to put in the standard deviation for the means. And we want to know the probability that it is greater than 26. And I got 0.1196. So the only thing different about what we're doing today is we have to do a little bit of work to find the standard deviation we're going to use. Did you get something different? Okay. All right, let's check the next one. And I never say this right. Is it Hereford or Hereford? Anybody know? Hereford? Cattle are one of the most popular breeds of cattle based on the data from the Cattle Society. The mean weight of a bull is 1135 pounds with a standard deviation of 97. That's talking about a population amount. So population mean is 1135. This is from years and years and years of data. And the standard deviation is 97. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So what are they saying our sample size is? 100. So N is 100. Is that big enough? Oh, yes. And we're trying to find the probability that the mean weight, that the average is less than 1100. Well, to find probabilities for our mean, for our average, we need to know the mean of the means and the standard deviation of the means. Well, mean of the means is just the mean. Simple duty. And standard deviation of the mean is the standard deviation divided by the square root of n. I believe that's 9.7. So this data, I should have made a note on the other one. This is what goes in the calculator. This is what goes in the calculator. So I'm going to back up, put the mean of 1135 and the standard deviation 9.7. And we want to know the probability that a cow, or the average weight of the cattle in 100 head of cattle is less than 1100. Ooh, I got 1.54, and then it says E -4 at the end. What does E -4 mean? Okay, so this really means 1.54 times 10 to the -4. That'd be move the decimal 4 places to the left. 1, 2, 3, 1, 5, 4. That's a really small probability. Now they asked us, is it unusual? So let's remember that from a previous unit, unusual probability, we consider it unusual if the probability is less than 0.05. So is this an unusual event? Yes. This is unusual. And otherwise, we're doing the same type of calculations. We're just putting in a different mean and standard deviation in the calculator, because you're finding probabilities about the mean. All right, that's all for 7.3. 7.4, we just put in proportions.